Welcome to the deep dive. Today, we're getting into something that for decades, felt more like science fiction than physics.
Well, absolutely.
We're talking about controlling a single quantum particle of light, a photon, and trying to bridge that massive gap between the quantum world and our classical one.
And this whole deep dive is built around the work of Serge Haroche and really the fundamental challenge laid down by the founders, Bohr, Einstein, Schrödinger.
Right.
They could describe the quantum world with math, but they couldn't, watch it. Schrödinger had this great line about it. He said all their experiments were like scrutinizing records of events long after they have happened.
A post-mortem, basically. You're always looking at the evidence after the event is over.
Exactly. A scientific post-mortem. So the goal, the holy grail, was to do an in vivo study. To watch a quantum particle live and breathe.
To catch it in the act without, and this is the key part, without killing it just by looking at it, which is what we're going to explore.
Yeah.
The photon box that finally made it possible.
This all falls under a field called Cavity Quantum Electrodynamics, or Cavity QED for short. It's all about getting light and matter to talk to each other perfectly.
And what's so cool is that there were two groups, right? And they came at this from completely opposite directions.
They did. You had David Wineland's group at NIST. They were masters of trapping atoms-charged ions, specifically, and then poking and prodding them with lasers.
So they trapped the matter and used light as the tool.
Precisely. Haroche's team at the ENS, they flipped that on its head. They decided to trap the light.
And use atoms as the tool. That sounds, harder somehow.
It was a huge technical challenge. They built this photon box, a cavity made of these superconducting mirrors that were so reflective. I mean, a single photon could bounce around in there for almost a tenth of a second.
Which, in the quantum world, is an eternity.
It's an incredibly long time.
Yeah.
And the atoms they used to probe that light, they weren't just any atom.
No, these are special, right?
Very special. They used rubidium atoms that were prepared in this bizarre state called a circular Rydberg atom.
Okay. What does that mean in simple terms?
It means the outer electron is in this huge looping orbit, really far from the nucleus. Think of it like a giant sensitive antenna. It makes the atom exquisitely sensitive to the microwave photons trapped in the box. They are, pretty much the perfect quantum sensor.
So you have the box, you have the photon trapped inside, and you have your super sensitive atom to probe it. But that brings us back to the main problem, the postmortem.
Right.
Normally, to detect a photon, it has to hit something, a camera sensor, your retina, and it gets absorbed. It's destroyed. How did they get around that?
This is the core of the breakthrough. It's a technique called quantum non-demolition measurement, QND.
Non-demolition. The name says it all.
It does. And the idea is that the atom doesn't actually have to absorb the photon to know it's there. Imagine the Rydberg atom is like a tiny, super precise clock, and it's flying through the photon box.
Okay.
The photons inside, they don't hit the clock, but their presence, their electromagnetic field, gives the atom a tiny, tiny gravitational-like nudge. It's called a light shift.
Wait, a nudge. So the atom just flies by, gets nudged, and that's it. How does a nudge tell you anything?
Because that nudge, that tiny shift in the atom's energy levels, it slightly changes the speed of the atomic clock. The ticking of its internal dipole changes frequency.
And the key is that it's non-resonant, right? That's why it doesn't just absorb the photon.
Exactly. The light's frequency is deliberately off from what the atom wants to absorb, so it feels the presence, but it can't eat the photon. Then, after the atom flies out of the box, they measure its clock.
And the amount the clock's time has shifted tells them how many photons were inside.
Yes, and the sensitivity is just staggering. A change of a single photon, from 0 photons in the box to 1, shifts the phase of that atomic clock by up to 180 degrees.
Wow, that's not a subtle signal. That's a huge, unmistakable flag saying there's a photon in here.
It's a massive signal. And because of that, they could count the photons n equals 0, n equals 1, n equals 2, without ever destroying them. They could watch a photon pop into existence in the cavity, live for a fraction of a second, and then vanish.
The birth, life, and death of a single light quantum. They actually did it. They beat the observer effect.
They did. And that's when things get even weirder and, more interesting. They started using this control to explore that blurry line between the quantum and classical worlds.
You're talking about Schrödinger's cat.
I am. They could use this setup to prepare the light field inside the box into a photonic Schrödinger cat state.
So not a real cat. We're talking about the light field itself being in two completely different states at the same time.
Exactly. Like a state where the field has one phase and simultaneously the exact opposite phase. a superposition of two distinct classical realities. Haroche even playfully called the single atom they used to create the Schrödinger kitten.
That's fantastic. And they could actually see the state. How do you take a picture of something that's in two states at once?
With a tool called the Wigner function. You can think of it like a quantum X-ray. It maps out the state and can show you these two distinct realities existing together with all the weird quantum interference between them.
And that let them study the great enemy of the quantum world,
Yeah.
decoherence.
Yes. The process where all this fragile quantum weirdness collapses when it interacts with the outside world, they could literally watch the cat state die.
So what did they find?
They found very precisely that the bigger the cat got, and by bigger I mean the more photons were involved in the superposition, the faster it decayed back into a boring, single classical state.
Which is the answer then. That's why we don't see quantum superpositions in our everyday life. They're just too fragile on a large scale.
It was a beautiful, direct demonstration of that boundary.
So where does this leave us? I mean, what's the big picture for this kind of technology?
Well, this ability to measure without destroying, this QND measurement, it opens the door to something truly powerful. Quantum feedback.
Okay, what's that?
It means you're no longer just a passive observer. You measure the state, you see it starting to decay, and you instantly send in another atom or a pulse to nudge it back into place. You become a quantum juggler, actively stabilizing a fragile state.
So you go from Schrödinger's abstract thought experiment in the 1930s to being a hands-on, deterministic quantum engineer in the lab.
That's the journey. And that's the provocative thought to leave with, really. This level of control, being able to tailor the energy of the system and repeatedly measure it to freeze its decay, that's the path forward. It's how we might one day protect these delicate non-classical fields long enough to build something truly revolutionary with them, like a quantum computer.